first of all, I'd like to dedicate the lecture to my very good friend John O'Neill, who, as we all know, passed away. I was there at the event at the IAS Cemetery with a few of those over here, and I believe Sarah is on Zoom. So if you are, Sarah, again, it's a great loss. I think that in behalf of everybody, certainly the IAS and the IAA and the astronomical community and that generally, that we really met him. He was a towering figure in amateur astronomy in Ireland, and well, I hope we give him a good send off on Saturday. So just to say that to start with, and I'll go straight into the talk then. Yeah.
There's no
laser pointer. Okay, where is the camera for Zoom?
Just stand where you are. You're fine.
All right, I'm not going to block anybody. Okay, so a lot of people wonder what the time will be. What's the best way to go forward?
Just pointing me out.
Right. Right. So, in case anybody came here wanting lectures on amphibians and cats and so on, a newt is simply short for a Newtonian. Cat is a catadioptric, which uses a combination of mirrors and lenses. I think most of us are fairly familiar with things like the Schmidt-Cassegrain. Spec is short for speculum, the old name for a telescope mirror made out of speculum metal. In other words, it's a reflector. OG is short for object glass, and that was the old term for a refractor's front lens, and thus it means a refractor, and you'll see an example of that later on. And there are various others which we'll come to. Huge variety of telescopes. When you really get into it, the number of different optical designs is scary. And then, of course, there are other varieties of observations in the other parts of the electromagnetic spectrum. And we'll look very briefly at those, but most of us are visual observers, and we'll concentrate on that. The very first, thank you, very first telescope was probably not used for astronomy. It's credited to Hans Lippershey, who applied for a patent in 1608 for an instrument to see things far away as if they were ready. And as you can see there, a simple refractor, convex objective, concave eyepiece, so we give an upright image. And he was Dutch, so it was called the Dutch perspective glass. And the word telescope was not coined until 3 years later, and it only had a 3 times magnification. Now, the interesting thing is that he may not have actually been the first, because his patent was refused, because there were other people who had also made telescopes. Now, he might have been the first, or he might not, but they're all right about the same time, but he gets the credit because he's the only one, or the first one anyway, for which there's an official record of a telescope. So, in the absence of any further information, that's him. But he wasn't the first one to actually turn a telescope to the sky, and it wasn't Galileo either, although a lot of people would say it was. Thomas Harriot, an English guy, there's the dates there. He made a drawing of the moon through a telescope with a magnification of 6 in August 1609, and that's 4 months before any recorded observation by Galileo. So Thomas Harriot has the honor of being the first telescopic astronomer. But of course, Galileo was the one who really brought the telescope into its own as far as astronomy was concerned. Probably most of you know a fair bit about him. It was iconic, not just iconic, the word's going out of my head, it'll come to me in a minute, in terms of his actual understanding of, good man, understanding of the universe. Did you take that off your car area? That's what I used to do. Right, thanks a lot. So he discovered the 4 main moons of Jupiter, called the Galilean moons, the rings of Saturn, although he didn't know what they were and couldn't resolve them properly, but it seemed that Saturn wasn't round the way Jupiter was. He drew the faces of Venus. He found that the Milky Way composed of innumerable stars and recorded sunspots, although Harriot had also done so earlier, and his drawings of the lunar craters showed that the moon was imperfect. And those had amazing consequences, because it challenged the church's view of the universe, that the universe was perfect, made by God, obviously, so it had to be, and that the earth was the center. Again, going back to the Genesis story, put the earth as the center of everything. And basically, that story said that the universe was created for man, and the earth was the center of everything. So that challenged not only the heliocentric theory, confirmed the heliocentric theory, challenged the old Ptolemaic theory that the Earth was the center. But in particular, since we were orbiting Jupiter, that meant that the Earth was not the only center in the universe. The phases of Venus could only happen if it was orbiting the Sun rather than the Earth. And the lunar craters and spots in the Sun showed that not everything in the Earth was perfect. Heavens was perfect. So the observations around the church, but the genie could not be put back in the bottle. And we know the rest of the story. His first telescope, very primitive, only 15mm diameter, focal length just under a meter, and magnification of 21, which is quite powerful, more than binoculars, but a field of view of only about 15 minutes. And the important thing is what he did with it. They changed the worldview of humanity by putting us no longer at the center of everything, and it led on to the cutting edge, top of the range telescopes that we have at the moment. Now, the next person we come to is somebody that we don't necessarily associate with telescopes, but Kepler didn't just give us the laws of planetary motion, he gave us a Keplerian design of a telescope or refractor that used convex lenses for both the object glass and the eyepiece, which is much better. And that led to a Dutch guy, another Dutch guy called Huygens, who developed very long focus telescopes of the Keplerian design. And the reason for that is, since it was just a single lens, there was a lot of what we call chromatic aberration. An ordinary lens, single lens made of any sort of glass whatsoever, doesn't bring light to focus all colors at the same time. And that's what's called chromatic aberration. I'm sure you all know that. But to minimize it, if you make the focal length of the lens very long, that reduces the chromatic aberration. And they came up eventually with these designs here, which must have been absolutely impossible to use. Never mind the flexure. Think of the slightest gust of wind and trying to track something as it moved across the sky. But at that time, that was the only way they had of trying to deal with chromatic aberration. And I think the longest one of those that was ever built had a focal length of roughly 150 feet. Now, if you managed to get something in the field of view in that telescope, it would have given you, with a reasonable lens, say 3, 4, or 5 inch diameter, it would have given you a pretty powerful view, but probably only for a few seconds at a time, as it would have drifted through the field of view. So they were powerful, but totally impractical. Now, a whole lot of twists and turns backwards and forwards from one design to another, as we'll see as we go along. The next person to make a significant contribution is James Gregory, who invented the Gregorian design, and that used a mirror, and that was very important for a number of reasons. First of all, a mirror, because the light does not pass through the glass, it's reflected off it. It has no chromatic aberration, and also you only have to curve one surface for the mirror, the front surface. It used an ellipsoid secondary mirror outside the focal point there. So this is basically like your Smith cast or your Gregorian cast. The light comes down the tube, hits a concave mirror, reflected back up to a secondary mirror, and then back down through a hole in the primary where you put your eyepiece. Since that secondary mirror is outside the focal point, as we'll see in a moment in comparison to the Smith cast, that means the tube is just that little bit longer. But there are quite a few advantages. So just going back to the story there, the first one was actually made by Hooke in 1677, and as we were saying, because the secondary is outside the focus, the tube is longer than the Cassegrain. One other point, and I wouldn't say they were easy to make, but they were easy to check for optical accuracy, as both the surfaces can be tested by what's called the Foucault test. And anybody, somebody like Jimmy, I'm sure, has used the Foucault test to test their telescope mirror. But the interesting thing is now they are now coming back into fashion again because they have advantages. The Magellan telescopes, which are huge, 2 6.5-meter mirrors. The LBT, Large Binocular Telescope, 2 8.4 meter mirrors. The Solar Telescope, the largest one in the world, 4 meter. And the GMT, which is being built, the Giant Magellan Telescope, with 7 8.4 meter mirrors are using the Gregorian design. So that goes way back to 1663. And it's just interesting that while it phased out for a while, it's now coming back in again. And I hadn't really realized that until I looked into this subject. So now we come to the one that most of us are probably most familiar with in terms of the optic ones. Sorry, this one isn't. Sorry, the Cassidy, not until you get to the Smith cast, is the optic. That used a design of a primary mirror, which was paraboloid, which is quite easy to make. Again, Foucault test that surface. The hyperbolic secondary isn't so easy to test. You really need an optical workshop to be able to test that curve properly with an absolutely perfect optical flat. But the advantage of that is that the secondary mirror is inside the focal point. It doesn't have to go through the focal point and then up to a point beyond it, the way the Gregorian did. So that means that your tube can be smaller. And quite a few telescopes like that were built as professional telescopes. Some of you may have got a chance to use the 16-inch one at our planetarium. There are various other ones around. And the biggest one that I know of, which was actually constructed, is that one there, the Strobel reflector at McDonald Observatory in Texas, which is 82-inch or 208 centimeter diameter. So pretty big. And one point I'll make about that, it is said there is public viewing at that telescope a few times per year, and some people say that is the largest visual telescope in the world. In other words, you can put an eyepiece at the back end and have a look through it, but we'll see competing claims for that later on, and I honestly don't know which is best. So it's only now that we come to Newton, and yet most people think of two main types of telescope, the refractor and the Newtonian. But it wasn't until Newton came along more than a century later that we get the Newtonian reflecting telescope. Again, because it has a mirror, there's no chromatic operation, only one optical surface, ignoring the eyepiece, obviously. So you're only having to do an accurate grinding and polishing on one optical surface. And it's probably the most powerful telescope type available to amateurs in the form of the big Thomsonians, which we'll look at later. So you're all probably fairly familiar with that. That's the classic design. The secondary mirror is flat. Most people, even if they make their own telescope, probably buy the secondary mirror because it's relatively hard to actually make a perfectly flat surface, and you can buy them relatively cheaply. The eyepiece is up near the top end of the tube, and that has advantages. If the tube telescope is relatively small, then the viewing position is quite a convenient height. But if it's a big one, some of them require quite a high step ladder to get up. If anybody ever looked through Jerry Maloney's 32-inch reflector, you had to go quite high up on the step ladder to get up near the eyepiece if you're looking at anything near the zenith. And some of the big American ones, they go up to about 1 meter and they're towed around on a trailer, and you really do need to get up high for those. And my memory for names is gone totally. Another guy who used a forklift truck to get the person up. Yeah, Eamon Ansberg, just couldn't get his name. Yes, he had a 36-inch, and you used a forklift to lift yourself up to the eyepiece, which was really neat. So he had that in Kingsland Observatory in County Roscommon, but he was due to move it to Spain. I don't know whether that actually happened or not. So now we come to the one that most of us are most familiar with, the Dobsonian, which is just a very simplified Newtonian. The telescope itself is the classic design, but the mount is very, very simple. Californian Buddhist monk John Dobson, some of us may actually have met him at one of the Whirlpool Star parties. Cheap, simple to make. It's great for visual use, and because you get a lot of aperture for a relatively small amount of money, it's great for paint deep sky objects and so on. Up to about 1 meter diameter, as I said, with a high step ladder. Transportable if you have it on a trailer. not suitable for photography, or at least not until recently, where you could simply put your smartphone up to the eyepiece and press the button. But in the older days, because there was no drive and because of image rotation and so on, then you couldn't use it properly for photography. There were ways around that with special computerized mountings like the Ponset and so on, but I'm not going to go into that. But basically that brought astronomy at a reasonable degree of performance and aperture and light grasp within the reach of more amateurs than ever before. And the Leviathan, the bird, which I'm sure we all know, is the largest Newtonian in the world that I am aware of. So 54-foot tube, and when you're up there in the middle of the night, 54 feet off the ground, it helps not to have a fear of heights. So it was made of speculum metal, which was basically something that was designed more or less specifically for telescope mirrors because it had a relatively high reflectivity, a mixture of 2/3 of copper and 1/3 tin, and that mirror weighed 3 tons. The whole telescope, 12 tons. It was very limited in observing because the telescope could only move between those two walls, but you had roughly an hour or so to observe any one particular object as you could track it across the sky. Because it was an antazimuth mount, you had to move it up and horizontally or down and horizontally at the same time. And this is really Ireland's greatest claim to fame, if you like, in astronomy. That was the largest telescope in the world from 1845 to 1917. Now, there were pros and cons with that. It obviously allowed you a very large aperture, but the mirrors tarnished, particularly in the Irish climate. And the way Lord Ross outlined that was to have 2 mirrors at any one time. One was in the telescope being used for observing, while the other one would have been in the workshop being repolished or, as necessary, sometimes recast, and then they would swap them backwards and forward. So very limited observing capability, but it was built to do one thing in particular, which was to resolve the greatest problem in astronomy at the time, the nebulae, the fuzzy patches in the sky. What were they? Were they actually stars that you couldn't resolve into stars, or were they clouds of gas, or what? And we know the answer now. He didn't actually manage to resolve that question, but he's best known for having discovered the spiral structure of M51, the Whirlpool Galaxy, and the shape of the Crab Nebula. And it was used, astronomers came from all over Europe to use it, and were quite amazed by the performance. But it didn't actually answer the question, but it did show, for example, that some galaxies had a spiral structure, which was something that you wouldn't necessarily expect just looking at the first place. So it is still usable in theory. That's me at Cosmos in 2016. Why am I up there? Well, it's a long story, but I was involved to a certain extent with the restoration. Michael Tubridy, the engineer in charge, who's a former member of the IAS, he may still actually be a member, was aware that I had an interest in various aspects of astronomy, and he asked me to help out on a few things like the meridian alignment and so on. So as a result of that, I got a sort of unofficial carte blanche to go and check out the telescope, and I led a group from the IAA to do various things to improve the performance in the tube and so on. I'm not going into all the detail of it, but anyway, I basically went in, and Nick Howes was there. That's his handle there. That's the thing, unusual thing there. Nick is in behind. And there were a few things that needed to be improved in terms of the trying to keep the mirror from getting tarnished and so on. So it is still usable, but the problem is that since it was refigured and the tube rebuilt and everything sort of returned to working order, health and safety people have come in on the act, and they're not too keen on, as I mentioned earlier, people standing up on platforms in sort of mid-air, 54 feet off the ground at night with no lights. There are other angles as well, that the ownership and responsibility for maintaining it have changed quite a bit. It's now under the control of the OPW, and they are not particularly interested in astronomy. The Burr Scientific and Heritage Foundation are still nominally the owners of it, but they have no control, no total control over how it's actually used. They do have a representative on the management board. There are moves to try and get it operational again. Peter Gallagher in particular, who's very involved there with the Rosses at LOFAR, is very keen to try and get it operational to some extent, even if it's only just pointing the telescope to a single point in the sky and letting the sky drift through it and letting people have a look through it, which is more or less what happened the first time I used it. But I've heard that story so many times over the last probably 15, 20 years, and nothing has actually happened. So I'm not holding my breath for whether that telescope should or will ever be used again. It's such a shame. A huge amount of public money was spent in restoring it. The new mirror alone cost £1 million. Well, I'll not go on. I can try and answer questions later if anybody wants to know. But it's a very sad story. But maybe the chapter hasn't closed yet. But let's go back to the refractors again. The whole reason that we sort of moved astronomy into the field of reflectors was that chromatic aberration was a big problem for refractors, but it didn't affect reflectors at all. But that was solved by Chester Moore Hall in 1733, who invented what we call the achromatic lens, a doublet lens, using flint and crown glass elements, and those two types of glass largely cancelled out each other's chromatic aberrations. He didn't actually make one, but he probably made one to test it. But the first proper telescope on that design was Dolland in 1758, and that led on to the development of giant refractors. The problem with speculum mirrors, they had a relatively poor reflectivity. Only about 60% of the light falling on the mirror would be reflected, and that would apply to the secondary mirror as well. So 60% of 60% is 36%. Bear that in mind when you are thinking of the Burr reflector. Only 36% of the light falling on the primary mirror actually makes its way through to the eyepiece, whereas a refractor transmits more or less all the light. There's a certain amount of reflection from the front surface and a certain amount of internal absorption, but basically you don't have that problem. So the Grubbs, as we know in Dublin, were leading telescope makers. They have telescopes all over the world, Northern Hemisphere, Southern Hemisphere, throughout Europe. They didn't really break into the American market, although they tried. They tried very hard to get the contract for the 36-inch refractor at Lick, but they lost out. I'm not sure exactly why. But the largest refractor in the world in the year 1880 was one that was built by the Grubbs, 27-inch diameter at Vienna Observatory. But in America, the Clarks built ever bigger ones, and the largest that was ever built and used was that 48-inch in Yerkes in 1897. And they then made what's called the equatorial mount, usually the German equatorial mount for a refractor. That was the standard. Now, there was a bigger telescope built, about 50-inch diameter, at the Great Paris Exhibition, but it was never actually used. It was just too big and unwieldy, and I don't think the performance was that good. So we now come to the one that took the record from the Leviathan, the 100-inch telescope at Mount Wilson in California. It was described as a Cassegrain, and it was in fact Cassegrain design. In other words, there was a hole in the bottom mirror, secondary mirror was up there, and you could put an eyepiece or an instrument at the bottom and use it at Cassegrain focus. It had a different type of mount called a yoke. You can only see one side of it there, but basically two parallel arms with the bearing of the north end and the south end. The disadvantage of that is that the telescope could not point to the pole. It could only go up to about there before the telescope tube would come to the north polar bearing. But it was very powerful. It was an equatorial mount. That means you could put a drive and you could take long exposure photographs, which is mainly what it was used for. And although it was Cassegrain in design, it was actually used mainly at the prime focus because you have a much wider field of view at the prime focus. And there's an observer's cage in there, which you can hardly see, but it was actually big enough for an observer to get into and be able to put in a photographic plate exposed for anything from 15 minutes to an hour or so, and then change the plate and put in another one. So it was mainly used as prime focus by Humason and Hubble, of course. And they found that M31 was another galaxy outside the Milky Way. So that resolved the question whether some of the nebulae were actually other star systems and not merely features within our galaxy. It's a long story here. I don't have time to go into it all, but by looking at the redshifts of different galaxies, it showed that the universe was expanding. And it was with that telescope, believe it is that far back, that Vicky found the first evidence for dark matter. We found that galaxies were rotating faster than could be accounted for by the amount of star and visible gaseous material in them. They also discovered that the seagates, which had been used for the distance scale up to that time, came in two varieties, if you like, population and population 2, and they had different characteristics. And when we find that the seagates that they've been using for the distance scale, the distant ladder, were actually not the type they thought, that in one stroke double the size of the known universe. So they had another galaxy, instead of being about 1.25 million light years away, became about 2.5 million light years away. And the point that I was making earlier, people say that you can still, on very, very rare occasions, probably if you have the very best of contacts in the astronomy world, and maybe a very large checkbook, that you can actually put an eyepiece in that telescope and get a look through it. Now, I've read conflicting reports about whether that is still the case or not. I don't know, but the likes of you and me probably won't ever get a chance to look through it. But either that one or the 82-inch McDonald Observatory, maybe the largest telescope that you can still look through. So this brings me now to one of the highlights of my astronomy adventures. I went to San Diego to board a cruise ship for the total solar eclipse last April. And San Diego was quite close to Palomar Observatory. And when I was starting off in astronomy, that was the mecca for astronomers. The 200-inch was basically twice the size, obviously, of the 100-inch. It was almost twice the size of the second largest telescope, but at the time, the 120-inch. It was just the biggest, best, most humongous, incredible telescope that was available at the time. And believe it or not, that was the first chance I actually got to do a visit. Now, I grew up, reading everything that was available about the 200-inch telescope at Palomar. I knew it was big, but when you actually get there, it is just humongous. It's mind-blowing. So a little bit about the background to it. The 100-inch showed what you could do. And George Hale, who's a wealthy, influential businessman, he didn't provide the money for this himself, but he persuaded other people to come up with money. And he planned one that was twice as big as the 100-inch in one stroke. The statistics are mind-blowing. The glass blank weighed 18 tons. 13 years of grinding it just to the rough curvature that they wanted removed 7 tons of glass, so it was down to 13 tons. That's even though it had a honeycomb structure, so it was relatively light compared with a solid piece of glass. Porter came up with a very ingenious design to get around the problem of the 100-inch not being able to point to the pole, so it couldn't see the whole sky. But what he did basically was to take the North Polar bearing and expanded it a piece from it, so it became like a horseshoe. So the bearing actually rotates. There's the rotating surface there, and can rotate around like that, and the telescope can swing right down into the cut-out part of the horseshoe. So that telescope was the first really, really big telescope that could point to the whole sky. So Again, although it could be used as Cassegrain, because they wanted as wide a field of view as possible for most purposes, it was used mainly at the prime focus. So there's the observer's cage there, and it's so big that an observer can get in there and sit in a chair and put in a 14-inch or whatever photographic plate and read a book or something for, well, no, we'll be tracking it. But in theory, you could read a book. You can get 2 or 3 people inside that observer's cage at once, but you'd have to be standing, but you're around the side of the secondary mirror. And that is basically where most of the wide field, relatively wide field images were taken at the prime focus. If they wanted really detailed images, they would use the Cassegrain focus, where you have your instrument down here. And that's probably a big spectrograph or something. And there's also a Coude focus, which I'm not going to go into in detail, but it basically diverts the light out through the one of the secondary declination bearings to a sort of a really solid pillar. And on that, then you can mount really, really big, heavy bits of equipment. You know, some of the giant bits of equipment that they have would weigh a ton or two. And the Coude focus has the advantage that it stays fixed, even though the telescope rotates around the sky. So prime focus and Cassegrain focus and Coude focus were all available on that. So the statistics, again, are absolutely mind-blowing. The dome alone weighs 1,000 tons, and the collecting area of them are 20 square meters. And because I know a few people in astronomy, Angela and I were lucky enough to get a personal conducted tour from the basement up to the top. And as I say, I knew the statistics, but when you see it, it really is just unbelievably big. 2 people can walk up side by side inside those arms supporting the North Horseshoe Mount. So if you ever get a chance, it's definitely worth a visit. It's no longer the biggest in the world by a long way, but it is still a huge, certainly in terms of physical size. So there's the prime focus. Yeah, there's the guy sitting in the chair and putting in a photographic plate or whatever in the prime focus. So aluminium coated mirrors, we've now got past speculum metal, because as I said, it tarnishes, and even at its best, it only has a reflectivity of about 60%. Aluminium coating, depending on just how you do it, and you know, I'm not going into the detail, but can get up in theory to 98% reflectivity, and that's a huge improvement. Originally, they used it mainly for just imaging, and then you add CCDs and photometers and spectrographs and so on. It can be used as an interferometer. It's now got adaptive optics, which I'll explain in a moment, and many direct areas of cutting-edge research, including the first direct imaging of an exoplanet, were done with that telescope. So a little bit about adaptive optics, because we'll come on to that later. You all know, if you look through a telescope, the problem of astronomical seeing. The image flickers, wavers, goes in and out of focus slightly, and that is due to the light from the object that you're observing coming through our atmosphere, which has different layers of different temperature, motion, different refractive index, and so on. And that basically is what causes the variation in the image. Sometimes it's relatively good, sometimes it's relatively bad. If you're in a high site, like some of the telescopes in Chile, where they've a very steady, what we call a laminar airflow, it's not too bad, but still it's never absolutely perfect. And adaptive optics are basically a product of the computer age and very, very fine advanced microscale technology. But what you do is, in the first instance, if there's a star in the field of view of the object that you're observing, you know that a star is a point of light. And if the image coming through is not a perfect point of light, but it's wavering, it's bright on one side, slightly fainter on the other, it moves slightly around within the field of view, you can correct that now by getting your mirrors in real time to counteract that. So putting it very, very simply, if the image of the star moves slightly to the left, you bring it back again, it tilts the mirror slightly the other way. It's a lot more complicated than that. But the point is that the computer intercept, or sorry, a special detector intercepts the light coming down from the star, and in real time it says to the computer, the star image is distorted in such and such a way. And the computer then activates not the primary mirror, but one of the secondary mirrors in real time to correct that, up to 600 times per second, the latest one. So that really is in real time. So that very largely gets rid of the poor seeing in the Earth's atmosphere. You can get almost down to the theoretical resolution capabilities of the size of the mirror that you're using. And that was one of the first telescopes to be used with that. Now, it gets more complicated than that as you go up to even bigger telescopes, and we'll look at that later. But that was one of the major steps forward in astronomical imaging and spectroscopy and so on. When we were also at Palomar, we saw the what was and still is the largest photographic Schmidt telescope in the world, a design from Bernhard Schmidt, a German astronomer in 1930, a very wide field of view. And it has a spherical mirror, which is relatively easy to construct. It has a specially curved correcting plate with a complex curvature. And you can see there that the mirror, the correcting plate at the front is smaller than the actual spherical mirror, because it actually bends the light slightly. That diagram is not strictly correct. Those yellow things should actually come out near the edges of that mirror. I've only just realized that. But the disadvantage of that is that you get an image right in the middle of the telescope, not very far in front of the main mirror, and it's impractical to put an observer in there. All you can do is put in a photographic plate, and it has to be a curved photographic plate because the actual focal surface, focal plane is curved. But nevertheless, you basically have an opening in the side of the tube, you put in your photographic plate, you close the door on the side of the tube, and you get your exposure. And it had very wide field of view compared with any other telescope. So it had used 14-inch square curved photographic plates. It was renamed after a guy called Oshin, who was donated a lot of money for an upgrade. And it did the famous Mount Palomar Sky Survey, which photographed the whole sky that was available to it, down to magnitude 22 in red, I think, and magnitude 23 in blue. And the Sky Survey comprises those actual high-quality photographic prints, 1,872 of them. Each one covers an area of the sky of 6 degrees square in red and blue. And I had a very interesting experience with that when I was, I never worked at Armagh Observatory. I was allowed to use the facilities there. And I remember on one occasion, there was a comet that had been discovered, and I knew the position, but there's no chart available for it, and I wanted to find it. And it was well below the limit of Sky Atlas 2000 or whatever was available at the time. But I thought, right, they have a copy of the Palomar Sky Survey in the Observatory Library. So we were allowed to go in and use the library from the same way Patrick Moore and myself. And I was there one night. And I said, okay, I'll just go and find this on the Palomar Sky Survey because the chart boundaries were marked off in right ascension and declination, and I knew the RN deck of the comet for that night. So you get a big base, basically a big box, and all the prints are there, and each one is actually a high quality photographic print. And you look up the index and you want chart 783 or whatever it is, maybe not 700, but whatever, might have been 783. And you then start to write, there was a grid reticule, transparent reticule that you placed over it, and you could trace off the RAN deck. And I opened it up and what's all this about stars down to magnitude 22, 23? There's not that many at all. How am I going to find this? And then I realized that in the little box alongside was a magnifying glass. And you put the magnifying glass there, and there were millions of stars that you couldn't see with the naked eye. The photographic print was of such high quality that the star images of the painted stars were too faint to be seen with the naked eye. And back then I had fairly good eyesight. So we used the magnifier, plus the grid, and you could then basically, I copied by hand basically a star chart to do a star hopping for the comet. But I was so disappointed when I looked at the photographic plane for the first time. There was maybe only 200 stars on it visible with the naked eye, with the magnifier there were 20,000 or something. Anyway, they now have converted it to have I got the slide for that? I think I have what's called the ZTF. No, I haven't. Right, I'll go back. Is it actually on the photograph somewhere? The ZTF stands for the Vicky Transient Facility. Anyway, you may have heard of the comet recently, which has a joint name of ZTF plus something else. And it's basically a huge, big box that is slung on the side of the 48-inch bit, and it is doing the same thing, but using now modern CCD type technology. I thought I actually had a photo of that, but there it is there, the ZTF's Vicky Transient Facility. In other words, it records anything in the sky that changes either in brightness or position. A 666 megapixel camera with a 46-degree field of view. And yes, there's the reference there, comet ZTF, whatever it was. So that was a fascinating thing to see as well. But sorry, just to complete the story, they then, because Palomar couldn't see right down to the southern hemisphere, they built a twin in Australia, another 48-inch, and then did the same thing of the southern sky. So the whole of the southern sky, and the whole of the sky, the whole 360 degrees and 90 degrees north to south is now the image of that. So the 5-meter, 200-inch was really near the size limit for a single mirror. And the Russians built one of 6 meters to try and get one up better than the Americans. The BTA, which basically stands for Big Azimuth Telescope, Big Telescope, no, Azimuth Mount. It never really worked all that well, possibly just too big for the seeing that was available at that site. I don't think it had adaptive optics. Maybe the optical quality wasn't all that good, maybe the pointing or the drive, whatever. It just basically was never a great success. And nobody ever tried then in Europe or America to build a bigger single mirror than the 5-meter. But the solution was to use multiple mirrors. And the original MNT, which I saw in Arizona many, many years ago, used 6 mirrors. That's not it, but it was that design. And again, with the advent of computers, it was possible to combine the images from the 6 individual telescopes into one image, as if it had the total collecting area of the 6 mirrors added together. And interferometry, in terms of interferometry, it had the aperture of the outer edges of the individual mirrors. And another effort now is the large binocular telescope, which we mentioned earlier. And with the benefit of the computers now, as I say, you can combine the images from multiple mirrors into one single image. So you no longer have to build a huge single mirror telescope. And that is up to now reached its zenith, if you like, in what we call the VLT, the Very Large Telescope. Don't blame me for the imaginative name. 8.2 meters diameter each, and they can be used individually. They can be used with the images all combined together, both for light grasp and for interferometry. And there are also these other smaller telescopes which can move on tracks, and that gives you a total interferometric aperture of 130 meters. So basically, with an interferometer, if your 2 mirrors are 100 meters apart, although you don't have the light grasp of the telescope in the 100-meter diameter mirror, you can combine the images from the 2, and that gives you the resolution as if you have a telescope of an aperture of 100 meters. It has, should have mentioned, Ritchie-Chrétien optics. That's basically another version, if you like, of the Cassegrain. There are a whole lot of new varieties now. Hyperbolic primary and secondary mirrors, with the benefit of computers and lasers now, you can make hyperbolic surfaces to a very high degree of accuracy, even with very big mirrors. And it gives you a wide field of view, which is free of all the aberrations, the spherical aberration, the coma, the chromatic aberration, others too that we need to go into. But the Ritchie-Chrétien design is probably the best of. I could get into trouble with people that make other ones. One of the best designs for almost perfect imaging over a relatively wide field of view. And being in the high desert, the Atacama in Chile, a very high, cold, clear, dry site. You can image into the infrared to a certain extent there because there's very little water vapor and very good seeing. And that also uses adaptive optics. Now, the next part of the story in adaptive optics is what happens if you're imaging something and there isn't a suitable bright star in the field of view, bright enough for the computer to be able to interrogate the incoming wavefront and see what the aberrations are. And the solution to that is that you make an artificial star in the field of view by shining a laser up into the atmosphere. And there's a layer in the atmosphere called the sodium layer, which is more or less what it says in the tin. There's a layer of sodium atoms at about 60, 70 miles up. And if you shine a laser with the right wavelength up into that area of the sky, it produces an artificial star. And you can then position that so it's exactly in the field of view where you want it, but obviously not obliterating the thing that you want to image. And that artificial star works in exactly the same way. The light coming down through the atmosphere interacts basically with that illuminated point or illuminated layer in the atmosphere. It doesn't know that it's not real, but the light then continues from that artificial star down to the telescope. And again, because it's passing through the atmosphere, it's distorted, and the computer again interrogates the wavefront from the artificial star, and it says that the atmosphere is distorting the image this way, that way, this microsecond, that microsecond. And again, in real time, it allows the secondary or tertiary or whatever it is mirror to correct for that hundreds of times per second. So the final image that goes to the detector, whether it's a spectrograph or a photometer, whatever it might be, the image is as near perfect as they can make it. And it gets even better when you go on later. So that's how adaptive optics works. If you've got a real star in the field of view, that's the best thing. If you haven't, you make an artificial star in the field of view using a sodium wavelength laser. And that brings us to what is currently the largest single telescope in the world today. Another very imaginative name is 10.4 meter diameter, and the name is the GTC, which stands for Grand Telescope Canarias, because it's in the Canaries, La Palma. A segmented mirror, 36 segments, adaptive optics. I'll say a wee bit about the segments in a moment. The maximum effective focal length is 170 meters. And that's even longer than the big, long aerial telescopes that they used in the Hungarian design. Ritchie-Chrétien optics, now almost standard. I'm saying almost standard. And as you can see there, all the big scopes are now on azimuth mounts rather than equatorial mounts, because again, now the drive available is so fine, you can sort of point the telescope to an accuracy of 1,000th of a degree, and the computer automatically drives the telescope across the sky at exactly the right rate, at exactly the right direction to counteract the rotation of the Earth and the changes in refractive index and everything. So you don't need an awkward equatorial mount. Now, just to go back to the segmented mirrors, again, you can't make a single mirror with a diameter of 10.4 meters. So the mirror is made in segments. And again, using the computer and responding in terms of the adaptive optics, each of those mirrors can be individually tilted and moved slightly so that they bring the light from the object to focus simultaneously, and then the adaptive optics take over and it corrects the wavefront of the light being reflected from the primary mirror. And that's really the way things go now for any telescope that's bigger than about maybe 4 or 5 meters. That is the single biggest one in the world. There are a couple of others that are almost as big, but that is the record holder. But to totally get rid of the problem of atmospheric seeing, you need to go into space. And we all know about the Hubble Space Telescope, 2.4 meter diameter. It can observe from the ultraviolet right through the optical into the near infrared. And I'm sure everybody here knows, you know, what it's like, what it does. More discoveries, more outstanding images than any other telescope at all. Although one is coming very rapidly on its heels. And you probably know about the Hubble deep field and the ultra deep field. And this is just one example. When it had imaged just about all the interesting objects that were available at the time, the director of the HST at the time, I think at any given stage, is allowed a certain amount of discretionary time that he or she can devote to something that he or she wants. And I don't know whether it was his own idea or not, but somebody suggested, why don't we point the telescope to the most empty part of the sky that we can find and let the telescope image for as long as possible to see just what is out there. And they picked an area in Ursa Major where basically, even with a powerful telescope, you couldn't see any stars. It just happened to be a very empty part of the sky. And they gave a total exposure of, we're using that telescope, of 1,000,000 seconds. Now, on your smartphone, you get an exposure of maybe a 500th of a second or a 30th, depending on the amount of light available. 1,000,000 seconds is a heck of a long exposure. But when they did that, they found basically that there were galaxies as far as the telescope could see. Now, anybody sitting near the back can't see, but that image is just full of galaxies. There are 1 or 2 stars which show up. Anything that has the spikes on it is a star in our own galaxy. I think there is one other yet, one there. But everything else there is a galaxy. So basically, the universe is full of galaxies as far as the eye can see, as far as the telescope can see. You might wonder why some of them are blue and some of them are red. In theory, at a large distance, they should all be redshifted, but that's another story. But anyway, very interesting. You see some very, very red ones there, for example, and there. And then James Webb has done the same thing, which I'll mention later. But we're getting near sort of the climax, if you like. Hubble showed what could be done. And the next step was the James Webb Space Telescope. It's the current king of telescopes. It's a 3-mirror anastigmat. Anastigmat means no astigmatism. So as well as having all the other advantages of a mirror, there's 0 astigmatism. And it's a version of the Ritchie-Chrétien design. It gets so complicated now in terms of describing the optical surfaces that I'm not going to even attempt it. It's in a special position called the L2, the Lagrangian 2 point, which is a way out beyond the Earth, away from the sun, about 1,000,000 miles away. That is because the telescope observes mainly in the infrared, and it has to be kept very, very cold. So they kept it well away from the heat that comes from the Earth and the Moon. And this here is basically a set of sun shields. So the sun will be down on that side of the telescope, and each of those shields acts as a heat insulator, so that practically 0 heat from the sun, even though it's shining on that side, gets through to the actual telescope. And on top of that, it has actual active cooling refrigeration, because sometimes they need to get some of the detectors down almost to absolute 0, not quite, you can't do that. And Tom Ray, whom a lot of you know at DIAS, was one of the principal investigators on one of the main instruments on the telescope, MIRI, the mid-infrared instrument. And if you followed the launch of that and the deployment of that, it was absolutely nail-biting of all the things that had to open up and move and click into place and be exactly aligned for the telescope to work. Was it 40-something different critical points of failure? And every single one of them worked perfectly. Anyway, A little bit about it. It's again a segmented mirror because you couldn't put the telescope as big as that inside the rocket that launched it. 18 segments. The final focal length is f20. The mirror is made of beryllium because of very low expansion. The mirror has to cool down. Gold coating, which is very good for reflecting in the infrared. And again, you could give a dozen lectures just on what the JWST has done. And it then imaged the Hubble deep field and ultra deep field again after Hubble, and looking in the infrared, it was able to see even more. One of the most amazing things is the effect of gravitational lensing, where that galaxy cluster there is bending the light from more distant galaxies beyond it, just like a lens. Einstein's theory of relativity predicted this would happen. So it's saying back almost to the edge of the universe, the Big Bang. Galaxies have been imaged that are only about 350 million years. They formed only, or they were at the stage where they were imaged about 350 million years after the Big Bang, which is giving the cosmologist a few headaches. That's the whole joy of astronomy. And we can't forget radio, particularly as we have an element here in Ireland, but you probably are all familiar with the big steerable radio dishes, like Jodrell Bank was sort of the pioneer for that for a long time. It was the biggest. It's no longer the biggest even of the steerable ones, but still a very powerful instrument. And then to go even bigger, you cannot really have a steerable dish that wouldn't get blown away in a strong wind. And the largest at the moment in the world is this one in China, half a kilometer diameter. FAST stands for 500-meter azimuth, because it's an azimuth mount spherical telescope, 500-meter azimuth spherical telescope. And it's basically a dish which is suspended in a hollow in the mountains. And although it can obviously only point straight up, the detectors which are mounted at the focus above it, they can be moved forwards and backwards, left and right, using cables slung from these pillars there. And by doing that, moving the detectors slightly, you can image quite a large area of the sky, not all of it. And the further you move away from the center point, the less the effectiveness of the collection, but nevertheless, they can cover, I think, something like 40 or 50% of the sky. So that is the largest in terms of radio telescopes at the moment, but there are other options, as you may well be aware. LOFAR, which brought Ireland back into the leading cutting edge of astronomy in terms of actual instrumentation and research being done on site. That's not too far away from the Leviathan and Mirror. The LOFAR, low frequency array, it can operate on its own. It's also part of this network, the International LOFAR Telescope Network. And again, using the principle of the interferometer, it can operate with an apparent aperture of that, which I think is about almost 2,000 kilometers in the east-west direction, not quite as much in the north-south direction, but there are new ones being added all the time. And the advantage of that is that it can operate 24/7. Doesn't matter whether it's daylight, nighttime, rain, maybe snow isn't quite so good, cloud, whatever, it doesn't make any difference whatsoever. You can do observations of the sun even on a totally cloudy day. It's very sophisticated, although again, it's fixed. In other words, the detectors actually point straight up. What they do is they have, again, very, very advanced and very powerful computing technique. And basically, if starlight or image from a quasar or Jupiter or whatever it might be is coming straight down, it will hit all of the detectors simultaneously. If it's, say, 40 degrees above the horizon, the light comes in at an angle. And therefore, just to take this particular set of detectors, first of all, the light will reach that detector before it reaches that detector because it's coming in at an angle. And the timing mechanisms and the time resolution and the computing power is so sensitive that it simply says that whenever a signal is coming then with that particular time delay, it is coming from an object up there. So you point the telescope. It's all the time the radiation is coming in from the whole sky all around it. But by choosing something which has a time delay equivalent to an object being 40 degrees above the horizon, you observe only that object. And it could be east-west, or it could be north-south, it could be anywhere in the sky. And basically, you're simply using the time delay for the signal coming in at an angle to decide, basically to detect what object you want. So if you're studying a quasar in a particular part of the sky, you simply tell the computer, look for signals that come from that area of the sky because of the time delay as they arrive at each detector. And then, of course, as the object moves across the sky with the rotation of the Earth, the computer allows for that. Very, very fancy, amazing technique. And there's two bands there, high band and low band antenna, and it's used for almost all areas of astronomy, from the sun to Jupiter out to the most distant galaxies. And if you haven't seen it, you really should go and see it. It's not so impressive to look at as the Leviathan. There's a very good visitor center here, and that tells you a lot about it. And Jeremy, any of the others basically will give you a very good guided tour if you make the arrangements. But I think the visitor center is sort of self-guiding. I've never been there on a just self-guided one. I've only been there when there has been an actual event. And the next step beyond that is going to be mind-blowing. The largest telescope in the world ever, and maybe for a heck of a long time, square kilometer array. It does what it says on the tin. The total collecting area of all the dishes will be a total of 1 square kilometer. Okay, it's being built in 2 sites, one in Australia, one in South Africa. There's the wavelength range, and it uses aperture synthesis and the phased array again, which is what I was talking about in relation to LOFAR. If an object is at that area of the sky, you simply detect the radiation, the signals that come in with that appropriate amount of time delay. And that's all you're doing. And you can cover the whole sky basically down to about certainly 15, 20 degrees above the horizon. And that will produce more data than the whole of the traffic on the internet at the moment. So the developments in astronomy now are limited more by data streaming and data analysis by the actual size of the instruments that are being used. But as we know, computers never stop, and they go on getting bigger and better and more powerful. There's fiber optics, and just reading something recently about a new way of transmitting large amounts of data in between the microwave and the ultraviolet band, which apparently is very, very effective in transmitting data over a long distance. There are problems which they say they are now overcoming. But this was another groundbreaking development, using gravitational waves to observe the universe. And again, you probably know at least the basics of this. Relativity says that if you have very massive objects moving rapidly through space, they will actually distort space-time and cause ripples in space-time. And if you have, for example, 2 black holes, which are very massive objects, orbiting around each other very quickly, that will cause ripples in space-time. And they finally managed to detect them with this LIGO, the Gravitational Wave Observatory, 2 stations, one in Louisiana, one in Washington. It's a long story, but basically by detecting the tiny, tiny distortions in space-time, because they're very, very small by the time they reach us from these distant objects, by detecting it simultaneously from the 2 stations, and again, not exactly simultaneously. That would only be the case if the source was directly above the halfway point in between them, but because the signal was coming in at an angle, they allowed for the fact that it would take very, very slightly longer to reach that station compared with that station. They were able to determine that it was from the same object. And there was also a detector in Italy which confirmed that it wasn't quite so sensitive, but it was able to confirm it. And again, the technology and the precision that is involved in detecting gravitational waves is absolutely unbelievable. Again, I haven't time to go into the detail, but that is nothing to do with the electromagnetic spectrum. It's using the distortion of space-time. And they've now discovered other things like colliding neutron stars, a black hole and a neutron star colliding, and there'll be much more to come. And we now refer to this as multi-messenger astronomy. There are two messengers. One is the electromagnetic messenger from the object, which would be, say, something like a supernova explosion or a hypernova. And the other messenger is the gravitational wave disturbance. And again, this is just the start of what's going to be available from that. So more gravitational wave observatories are being built. That gives you more detections and better location of the source, because the more different sites you have observing the same event, the more accurately you can say that came from a particular object in the sky in that particular right ascension and declination. And then you point your optical telescopes or gamma ray detectors or whatever there to see what was happening there. Now, in the future, this is interesting. Again, why can't astronomers come up with better names? The EELT, E for European, and ELT, Extremely Large Telescope. And that's what it is. A 39-meter aperture when you count all the segments, 798 individual segments. Again, it's the three-mirror and astigmat design, which is basically Richard Christian. And it has what we call multi-conjugate adaptive optics. And the difference is, compared with ordinary adaptive optics, that mirror is sampling a column of light coming down from the sky that is 39 meters across. Okay, if you like, a column of light. And the atmosphere varies over that scale. So one side of the mirror will be seeing atmospheric distortion totally different to atmospheric distortion on the other side of the mirror. And therefore, they're going to be using 4 pairs of guide stars so they can sample different areas of the sky around the object that they're observing. And that will correct not the 798 individual segments, but again, I think in this case, it's the tertiary mirror in the system will correct in real time for the distortions coming down that beam and that beam and that beam and that beam in real time simultaneously to give you an almost perfect image at the detector. And that is basically mind-blowing. It really is hard to get your head around it. And of course, the individual segments, apart from the adaptive optics element, the 798 individual segments all are computer controlled so that they all point to exactly the same point of the sky. Once you get that, when they're started observing, that's when the adaptive optics comes in. They correct for the distortion in the atmosphere. And there'll be quite a few spare segments. So at any given time, you may have a couple of segments taken out for cleaning or re-polishing, re-illuminizing, whatever. And you have other ones that you put into space and into their place. And at any given time, the whole telescope surface, the individual mirrors will all be replaced and cleaned and recoated on a rotating basis. So that is due to have first light in 2028, which is coming up to only 3 years away, although there can be delays. Now, why 39 meters? Why not 40? Does anybody know? I think John knows, maybe not. No? Any fans of the Hitchhiker's Guide to the Galaxy? What's the answer to life, the universe, and everything? 42. Originally, they thought we'd make it 42 meters in diameter. When they looked at the actual practicality of having an extra ring of mirrors the whole way around, they were going to go over budget. It was going to add an extra degree of complexity to the whole system. And very reluctantly, they decided we're going to remove a complete ring of the outer mirrors and that brought it down from 42 to 39. Sad story. It would really have been lovely to have it either 40 or as a tribute to Douglas Adams to have it as a 42-meter telescope, and that would have given possibly the answer to life, the universe, and everything, because it would have been so bloody powerful. So I think we're coming near the end. Oh no, there are two new ones. I have to put this in. You're all probably aware that for a long time, women were subject to the so-called glass ceiling. It was hard for women to get their way to the top in any of the sciences, and that included astronomy. And yet, throughout the history of astronomy, women have played major roles from Caroline Herschel onwards, and we have a very good lady. Is she right? Hillary. But they're now being recognized. The two new telescopes coming along, apart from the ALT, are both named after women. There's the Vera C. Rubin Observatory in Chile, and that is basically going to be a new version, if you like, of the Palomar Sky Survey. It won't have quite as wide a field of view, but try and get this into your head. It's going to photograph the entire sky every few minutes. Everything in the sky down to about magnitude 25 or something like that. Again, a version of the free mirror and astigmat design giving a wide field of view, and the largest digital camera in the world, 3.2 gigapixel. I don't know how familiar you are with computer terminology. 250 teraflops of computing power. Now, tera is beyond, I get lost, there's giga and it's 3 orders of magnitude by powers of 10 beyond giga. That is the, petabytes, gigabytes. Oh, I got lost. Anyway, terabytes, yeah, huge amount of data. And as I said, in relation to the square kilometer array, the amount of data it produces is going to really be straining all the systems available to transmit it and analyze it. 10 million alerts every night. Now, some of those are ones that we know about. We know, for example, there are variable stars. We know that there are asteroids moving. We know that there are comets moving and so on. But basically, the computer software will automatically sort of put all those to one side and archive them. So the computer will then only send on for actual analysis only the interesting ones that we don't expect. There's something moved there and we didn't know it was going to move. Something changed brightness there and we didn't know that was going to happen. So each alert, there'll be 10 million alerts every night. Each alert will give the actual details of the what actually happened, where it is and what happened. A time series of up to a year of all the previous detections of that source. So if it's a variable star, it will give you the light curve for the whole of the previous year. If it's something moving, it will show you what has moved over the year. And they expect it to detect 90% of all of the near-Earth objects, which are 300 meters or larger, 10,000 Edgeworth-Kuiper belt objects, which are the ones out beyond the outer part of the solar system beyond Pluto, thousands of supernovae, and the distribution of dark matter. And that will be available free, instantly, in real time to everyone, because no one group of astronomers could attempt to analyze that all themselves. So I'm not sure who actually is funding that. It's probably a consortium of American universities or something like that, but they decided that there's no point having all this information coming in, which is far too much for us to analyze. It's going to be made available to everybody throughout the world, real time. So if you want to, and if you have the computing power, you can get straight in and get the data. The next one is the Nancy Grace Roman Space Telescope, and it's going to do a bit more than Hubble or JWST. It will also look at the infrared. It will also be out at the Lagrange true point to get well away from the heat from the Earth and so on. Planned for 2027, the same diameter as the Hubble, but only about a quarter of the mass. And unlike Hubble, it will operate in the infrared, and it will have a much wider field of view than the James Webb, but again, it will be surveying in the infrared. And the advantage of the infrared is that infrared radiation penetrates through dust and so on, so you can look right through to the center of dusty galaxies. It also looks way back in time, but because of the expansion of the universe, light from very, very distant objects is very considerably redshifted. So again, like James Webb, it can look back at very, very old objects, very, very far back in time. And exoplanets, oh yes, this is interesting. It's going to take a coronagraph, use a coronagraph, which blocks out the light from the star so that you can see the planet orbiting around the star 100 light years away, whatever. Hard to get your head around that, but that's what it's planned to do. And it will not only image those planets directly, but it'll be able to take their spectra. So that telescope will be monitoring 100 million stars for hundreds of days, and expected to discover about 2,500 new planets, not ones that happen to transit in front of the star, but any planet that happens to be around those stars. And there may well be, they expect that there be rocky planets like the Earth in regions that may support the existence of liquid water and therefore possibly of life. So, near the end, this gives you the relative sizes of some well-known telescopes. That is the extremely large telescope there. There are two others that may or may not be built, which are almost in the same class, the 30-meter telescope, which is what it says, and the Giant Magellan telescope. That one is planned for Chile. I think it's actually under construction. That one there was due to be built on Hawaii, both American. The problem is that the mountain is sacred to the Hawaiian people, and there are serious objections to them building yet another big telescope on top of the mountain, and that development of that is frozen at the moment. The other important thing is that Congress has only approved enough money for building one of those. And since that one there seems to be stalled, the more likely one to be built is the Giant Magellan Telescope 2029. So that's 2 years after the ELT. Now, as I say, I think that's actually underway. But just a little bit to try and get your head around. When that is built, it is going to have a greater light collecting power than all the other large telescopes that currently exist put together. So we have the Grand Telescope in the Canaries, the twin Tech telescopes, which are 10 meters each, the Gemini North and the Subaru, which are basically twins of each other, which are in the 8-meter class, Gemini South, Vera Rubin isn't up yet, the VLT, and is there one other? Oh yes, the Hubble Everly telescope and SALT, which are like the GTC but slightly smaller. That will have more light collecting power than all of those put together, which is sort of mind-blowing. Now, a few others just for comparison. There's the Yerkes refractor there, 48-inch, the big Grand Paris exhibition one, which was built but never used. The 100-inch Hooker, the 200-inch Hale, the MMT, which is now sort of changed. Oh, I'm not going to it, but it's no longer multiple mirror. Oh, I forgot the LBT. You add the LBT in to the other ones, and it still won't have the total amount of light collecting power of the ALT. That was the big Russian one. There's James Webb, there's Hubble, the Magellan ones. They come into it as well. Now, it doesn't show the Leviathan, but it would be roughly halfway, well, not quite halfway. That's the 40-inch, and that's the 100-inch. So the 72-inch would be roughly halfway along in size between those. And this big outer one here was a lovely pipe dream, the overwhelmingly large telescope, or OWL for short. And they are not going ahead with that, certainly not at the moment. So that sort of shaded this there would have been the size of a 100-meter diameter, obviously multiple segmented mirror. They thought about it. They did some figures, they did some planning, and said, no, not possible at the moment. The Arecibo dish, which was the largest radio dish until it collapsed a couple of years ago, has now been superseded by the big Chinese one. That's the curvature of it on the same scale. Oh, and there's the 500-meter spherical radio telescope, and a basketball court and a tennis court for comparison in size. So it's come a good way from Galileo's little thing that size. Now, one more, I think, just final slide, which I thought I had to put in. Oh, yes, I forgot about these. Yes, this is the future. Oh, dear. It always hurts me to say this because I like looking through an eyepiece. These electronic telescopes, which basically are a live CCD imaging, which builds up the image continuously as the object is tracked across the sky. So it's like a video building up an image more and more and more, and you can do all sorts of things with it. You basically look at the image on your smartphone or your computer screen. There are others available, Unistellar, Lux, Leonis, and so on. They're small, but they're incredibly powerful. They're easy to use. I don't know if anybody here has one, but basically, as I say, it hurts me to say it, but that is the future for amateur astronomy. They're now building bigger ones. They started off with a 50-millimeter, quite expensive. There's now a 30-millimeter, a lot cheaper, which does almost as much. And I'm sure it won't be long before there are even more powerful ones. And with a bit of competition, then they'll get better performance and lower prices. But just to show you that I'm not making it up about all, and I think I showed this slide was shown the last time here as part of John's talk. You really do, when you're using the refractor, you write OG instead of refractor. So it's the 10-inch refractor at our observatory, and that reason I'm showing that is that was the invisible side of Saturn's rings back in 1966. The sun was shining from that side there, and that would be the north side, because inverted image, and the Earth was on that side, and yet you could see the rings, which was quite an interesting experience. Saturn's rings are once again at the moment closing down to the point where they will be edge on as we see them from the Earth. They'll be disappear from a while next spring, and when they reappear after solar conjunction, round about May maybe, you'll start to see the other side of the rings. But I didn't make Og up. It really is what you see. And if you look at Lord Ross's notebooks, for example, or other people of that era, and they're describing what telescope they wrote, it would be 72-inch spec. So they did talk about specs and Ogs. So I think that is the last one. Right. Thank you very much.